In this presentation, we're going to discuss a very important topic, something that in aerospace we refer to as space junk. But what is it? In this image of Earth, we see an artist's impression of space junk orbiting it. It does give us a sense of just how dire it is that we take care of not just what's on the Earth, but also what's orbiting the Earth. Space junk can be broken down into two major parts. Things that are natural, like comets and asteroids, and things that are artificial, like satellites that break apart, or tools, thermal blankets that get lost out in space from spacewalks, or things that fall off of spacecraft that are in orbit. This can even be human refuse. The waste has to go somewhere. They can't keep it on the ISS. The image that you see here is of the Vanguard satellite, which was US's first satellite launched in 1958. It's technically considered space junk as long as it's non-operational floating around out there. These are some basic statistics. There's 28,000 objects that we've created that have gone into some type of orbit since 1957. 9,000 of those are still in orbit, and only 550 of those are still useful. We have over 75 launches per year, and now with SpaceX launching so many Starlink satellites, we're launching more and more every single month. Every year we have more objects in space than we know what to do with. Here we can see a static image simulation of space junk as of 1967. 50 years later in 2007, it looks more like this. On PLTW's website, under 3.1.3 Space Junk Mitigation, we have some videos that walk us through this simulation. Here's a 34-second video of what it was like for 1957 space junk. Obviously, the little purple dots are a bit exaggerated in size, but it gives you a sense of just how much is actually out there orbiting our planet. And here it is in 2007. Notice the geostationary orbit, a larger ring outside that's fairly thick, and all of the satellites that we've put into orbit there, plus any and all of the space debris and junk, including the low Earth orbit stuff that's much, much closer to the Earth. And with this video, we can see a trend from 1957 to 2011. Watch it grow. Sputnik, and then all of a sudden, everything else. Pretty steady climb into the 70s, crossing into the 80s, a little bit of a dip. Star Wars starts to become a thing, and I don't mean the movie, I mean the program. Get into the 90s, and all of a sudden, GPS is made available to people. Then we start getting into cell phones. And look at what we have now. So much more. And we're launching even more. We're only at 2011 in this graph. 10 years later, you should look up Starlink and see what that's going to be like. So the question becomes, is this dangerous? And in a low Earth orbit, where it is probably most dangerous for us, you have LEO debris that's traveling with the equivalency of the energy that a car at 55 miles would have if it struck something, or a bowling ball at 300 miles an hour, or a 60-pound safe at 60 miles per hour. Things are traveling around in orbit in LEO at around 18,000 miles per hour. That's 7 kilometers a second. That is fast. You may ask yourself then, how long will these things actually stay in orbit? I'm not planning to leave Earth anytime soon, so as long as it doesn't fall back and hit me, I'm okay. Well, distance relativity is important. Anything that's 250 to 600 kilometers, you're talking about 150 to 375 miles up. This is low Earth orbit, where things like the shuttle and space station are located. And yeah, that stuff is pretty far away from you, but it's not far away from other things in that orbit, and when those strike each other, it's a problem. Things that are less than 200 kilometers away, they'll stay in orbit for a few days if they're not maintained. Things that are from 200 to 600 kilometers, that's going to be a year. Things that are 800 kilometers down to about 600, you're looking at decades. And things that are greater than 800 kilometers, it's going to be centuries before it comes back to Earth. And things that are 36,000 kilometers, well, this junk is going to be out there forever. Think of it like this. 20,000 kilometers away, that's 12,500 miles up. The distance there is basically where our GPS satellites are. 36,000, which is roughly 22,500 kilometers up, you're looking at the distance for geosynchronous satellites, which are used for things like communication and television broadcast. That's that big ring around the outside. Lots of stuff out there. Lots of stuff really far away. Lots of stuff really close. Some of it's going to stay for a long, long, long time, if not forever. And some of it is going to come crashing back before too long. Which means we need to track it. There are several tools used to track objects. Monitors on board spacecraft can track objects that are smaller than or less than 0.1 centimeters in size, of which there are millions each, with the potential to cause significant damage to spacecraft. Telescopes and radar tracking, however, are more than around 100,000 objects, and they measure over 0.5 centimeters in size. Optical tools can track objects larger than 10 centimeters, of which there are around 11,000 of those things. There is a multinational effort to help keep track of space junk. Organizations like NASA's Orbital Debris Program and the European Space Operations Center. These organizations provide advice about orbit changes when it looks like there's going to be a collision. There have been incidents where objects have struck one another in space, in orbit, but it's important to note that the risk to individuals is pretty low. About 1 in a trillion will get some kind of injury from orbital debris. The risk due to lightning strike as a comparison is around 1 in 1.4 million, or at least as of the creation of this presentation, that was the annual risk in the United States. One person has been known as of the creation of this to be struck by debris, but not hurt. Things do fall back to Earth. Here we can see a South African land strike. This object was orbiting the Earth, and this is where it landed. Here's another example. This is Texas in 1997. This hunkin' piece of metal fell out of the sky. And here's a picture of things that have been found in places like South Africa as well. This is taken as of 2000. Something did strike, and often does, things like the shuttle window. This is from STS-94, so this is a space shuttle mission. And this is an up-close view on the left side of a micrometeorite or micro debris that did penetrate part of the space shuttle window, and you can see it from a further out view in the image on the right. And that's why these windows on things like the space shuttle and the International Space Station are extremely thick, upwards of even 12 inches in some places. And that's very, very thick glass, but these things are traveling at tens of thousands of miles per hour. In 1978, Donald Kessler famously wrote about how space junk may have catastrophic impacts if it collides with other objects. Satellite collisions could generate lots of fragments. Fragments can cause exponential increase in those collisions. The growth of our debris belt would grow horribly. Potentially, this could block other craft from that altitude or even from above. On February 10, 2009, the Iridium 33 and the Cosmos 2251 satellites collided with a velocity of 11.6 kilometers a second at an altitude of around 790 kilometers. The collision was catastrophic, likely producing hundreds of fragments large enough to catastrophically break up other satellites and tens of thousands of fragments large enough to damage other satellites. This is the first clear example of what was predicted in 1978. The simulation that you're about to watch is of the Iridium and Cosmos collision. It shows the debris itself as the satellites smash into each other. The satellite collision is based with an evolved statistical breakup model. This 1-minute video demonstrates the approach trajectories of the two satellites prior to impact, as well as a statistical breakup model with an example of propagated debris. This is a 1,000 object statistical sample of more than 2,600 fragments predicted using a modification of the NASA Evolved Debris Model. This model abstracts structural and material fragmentation physics. Outcomes depend on the degree of contact between the two satellites, distinguishing between portions totally involved and those outside the contact area. This depiction uses initial on-orbit masses of 685 kilograms for Iridium and 900 kilograms for the Cosmos 2251 and assumes 30% direct contact for each object. The model can also release instantaneous energy stored in unexpected propellants, although that capability was not used in this particular case. This image depicts an impact risk model of the ISS. This is probably our most worrisome object in space. This is where we house quite a few people at one time, and it's getting bigger. The debris from it is a bit of an issue, but also debris hitting it is even more of an issue. We probably need to consider a few things. One, limiting our creation of space debris. We need to limit explosions in space by making sure we use better equipment. And we need to consider a graveyard orbit above a popular geosynchronous orbit known as GEO or GEO. We also need to find ways to clean up our messes. Some way for us to recapture the objects that are out there and do away with them, or put them at a particular angle as they enter the atmosphere to burn them up. There is a mess out there, and we need to figure out how to take care of it.